Sun is relatively stable, a type of star informally known as a yellow dwarf. It is middle-aged and has not changed dramatically for the last 4 billion years. We can be glad our Sun is as stable as it is. As unlike most other stars, the energy it adds is fairly constant. If you were to look at footage of the Sun taken by the Solar Dynamics Observatory. However, you would quickly realize that even one of the most stable types of star has a landscape of activity. Sunspots, solar flares, and coronal loops are present every single day on the Sun's surface. Could say the surface almost appears to be fluid, but the Sun is neither solid liquid or gas. It is rather a giant, nearly perfect sphere of plasma, is composed of mainly hydrogen and helium, and at the center of the Sun, due to its enormous mass, nuclear fusion, takes place at the Sun's core. Hydrogen atoms are fused together under immense pressure to become helium. The sound itself, I tend to think of it as an onion ballet, consisting of different players, so in the core, the very center of the Sun essentially, that's where nuclear fusion happens. Now you have to think. So essentially, the Sun is kind of huge bowl of plasma. You know, soup of particles. You know, ions, atoms, electrons, sort of everything mixed up together. On average, it takes a photon to travel through the radiates on something like 170,000 years. It's D-dance. And then from that, it then hits the convective zone. So everybody knows that hot air rises and cold air falls. So what then happens is the material is very hot at the bottom near that radiator zone. And then it expands and it rises to the surface, and that's the main transfer of the heat from that point onwards. Obviously then glowing from the surface, like any hotter material does, plasma is an extremely good conductor of electricity and is also affected strongly by magnetic fields. So sunspots are actually the surface representation of the magnetic fields of the Sun. So the magnetic fields actually get very tangled below the surface. So between that radiative zone and the convective zone, the magnetic FS get tangled. They tend to appear in pairs, in groups. I mean, if you think sort of a magnet, you have positive polarity, negative polarity. I mean, that sort of normally would be seen sort of in sun-pet pair, you know, one would be positive, the other would be negative, so. And normally, of the strongest magnetic fields that we observe are in the sunspots. The sunspots can be anywhere from about 15 kilometers in size to around about 160,000 kilometers, so multiple times the size of the Earth. Sunspots can often be seen at the base of various solar phenomena. Coronal loops, large rings in the Sun's music atmosphere, prominences, large, bright gaseous features extending outward from the Sun's surface, bridging into space for thousands of kilm, music, and solar flares, a sharp increase in the Sun's brightness and temperature. Solar flares tend to happen over active regions, and optive regions are essentially as sunspot groups. So these are the locations where definitely see the strongest fallies. So, reconnection event is essentially what produces the energy that causes both flares and CMEs, because the convective zone is very turbulent. Many of current simulations show that most of the magnetic field as it rises through the convective zone is being destroyed. You know, being diffused around its more complicated magnetic structure, such like twisted magnetic fields that tend to survive, and so you can imagine, so especially of over large sunport groups, we do see very complex magnetic field configurations. Magnetic fields so twisted, rayed, basically creating this complicated geometrical topological structures. And it's within that structures that magnetic fields and magnetic energy is stored, and what happens during reconnection. So I tend to describe it. Think of the magnetic field as a rubber band, so you twist it, turn it, and then basically at some point you pull it too strongly and it breaks. And that's essentially when we have the reconnection event. And what happens during the reconnection event, essentially, as the name suggests, the magnetic field lines reconnect. And when that happens, you get a lot of energy being released, of the order of millions of nuclear weapons, nuclear bombs, all in one instant. And that energy will produce both solar flares where large amounts of radiation is released, and also potentially led to large-scale movement of the material that was suspended in the prominences. Both towards the sun and away from the sun. When that reconnection event happens, then, again, the material which is suspended in those magnetic fields normally will move one way or the other. A lot of it will move back towards the sun, often following those magnetic field lines. So moving to the footprints, like, for instance, move to the sunspots, if that's where the footprints are, but equally, in the middle of those magnetic fields, quite often a bubble of material is essentially ejected away from the sun. And so what you'll end up having is millions of tons of charged material flying out from the sun, relatively fast. Over the order of hundreds of kilometers per second to thousands of kilometers per second. And those are what we call CMEs, Coronal Mass Ejections. These CMEs come in contact with the planets all the time. Venus, when faced with a CME, has its lighter particles stripped away in the higher reaches of the atmosphere by the force of the ejection. This